So thank you for the introduction. So yes, as she said, I will talk about this Industry 4 and how to embrace 3D camera technology and a couple of things you need to consider in order to use it to improve productivity. So as you all know, there is an ongoing fourth revolution, industrial revolution, which is all about automation and connected systems. And a part of that is equipping robots with 3D vision and more advanced vision system in general to make them more capable of doing more advanced automation. So it's about ease of use, speed and reliability, like things that's important for in all kind of applications. But previous it has been a lot for bigger industries, right? The third industrial revolution and what we have seen of lots of automation happen in the, for instance, in the car industry, where they have a huge line where lots of products go through, and it was kind of set up for automation in general, right? So a lot of the industrial robot, is working in those kind of environments. But there is a new thing we see, and that is these smaller robots, these so-called collaborative robots, that also are deployed into small and medium enterprises and doing work there as well. And one thing you can observe is that lots of the bigger robots, they often handle bigger objects, right? So it could be that they lift the roof on a car and place it on an automobile, or they do welding on these kind of big objects. And then the need for very accurate vision is not as high, at least for those picking and lifting and these applications. Of course, you have inspection application where you would need very high accuracy, but in general, when you have big robots, then you didn't need as accurate vision. But when you go into this new area where you have smaller robots that do a variety of tasks, the objects tend to be much smaller as well. It's kind of obvious because the robot can't lift that much, and it has to handle smaller objects, right? So, and then that requires more of the 3D vision system. So you need more accurate vision for smaller objects. So there is a need for a highly accurate 3D vision in the emerging field of collaborative robots. And as of now, the most major thing is around this picking and placing. I mean, there is also, of course, in inspection, but what is different with picking and placing is that now it starts to become more generic solutions, like a picking system that you can buy and you can apply it to your operations with minimal teaching and kind of like more standardized sort of products, right? From earlier where it was more project-based, where there is some sort of task and then you hire an integrator and they do a work for you and kind of specifically make that system. Now it's more generic. But those systems use 3D cameras. And when you look at the 3D camera market, there is so many different technologies out there, but they all are made for specific types of tasks. And they deploy different underlying measurement principles, which are good for different types of tasks. And a very simple illustration of this is if you have the required accuracy here, so from 10 to 100 micron, 1 millimeter to 5 millimeter, and 1 centimeter plus, and then you have distance on that axis, you can kind of broadly categorize inspection metrology, very high accuracy, automated material handling, reach of a robot arm, and then like farther away, it's more about navigation, people monitoring, obstacle avoidance, so on. And the different technologies, like broad sense, of course, is stereo and time of flight. They are working very well in this kind of region and kind of going, in some cases, down here. And then you have laser triangulation and time-coded structured light, which operates here and can also go down to very accurate systems for metrology, for instance. So, yeah, you can think that they operate best in this region here, out to a certain distance, but then other technologies start to become better, right? So there is no technology in 3D vision that fits every task. So you have to see what sort of task do I have? What is then the best technology for that? So I will talk about structured light, and I will talk about picking and placing in the medium to small range. So like out to 2 meters or so, maybe 3, but yeah, kind of in that range. And then there is accuracy. So it's quite complex field actually. And so what is the kind of overall thing you need to consider? So there is 3 things to keep in mind. It's like very simplified if you think of a bullseye and you're throwing darts. Then the precision will be, if you look at it on this axis here, if you throw several darts after each other and they happen to end with big distance in between them, then you have a lousy precision. So it's like kind of the repeatability, how close are they together. So if they're very close, then you have high precision. It's not necessarily right. It's not in the bullseye here, but it's very precise because it says the same every time. And then you have another, and that describes the random errors of a system. And then you have the so-called trueness, which is the systematic errors. And that is same here. You can have a big spread around the bullseye, but the average of these measurements ends very close to the real reference. And here the average will end up a distance from the reference, meaning you have low trueness. So you have these 2 axes, and when you combine those 2 things, then you have accuracy. So it means that you need to have very high repeatability, and you need to have a high hit in regards to what is the true reference. And this is very important because when you see a specification sheet from a company, then you can talk about these terms mostly very loosely. It can be like accuracy on a board, like calibration board. But then it's always a relative accuracy. It's accuracy related to a certain system. And that could be a calibration board. It could be like these spheres. You measure the distance between them and so on that they use in metrology. But it's important that it's not absolute accuracy, it's relative accuracy. And for a robot, the concept about absolute accuracy is very important because you are actually going to tell from the camera where the robot is going to move. So if that's not entirely correct, and even if it's very repeatable, but it's wrong, then that can end up in collision. So it's important to have all these terms in order and understand them and see what the different cameras give you. One example, for instance, is with time-of-flight technology, where because of a multi-beam thing, how they send out light, they have a tendency to bend the reality a little. It's fine when you do gesture recognition and things what they were made for, but it's not so good when you want to do an accurate operation with a robot. So this is what it means in 3D. So if you have, let's say you have a flat target here, and then what the 3D camera gives you is kind of like this bended view of the world, then the trueness will be kind of how much is this different from a flat plane, and the precision will be what is the spread individually, like locally here. And if you combine those 2 together, you get the accuracy. And highly accurate will be very true to reality, with little noise. Yeah, and of course here is a scenario where this thing matters, because you have a bin with a lot of objects, they are close together. You understand that you need to place the finger of the gripper properly, or else you can cause collisions, and the information you get from the camera becomes very important in these kind of scenarios. And then accuracy counts. Another thing you need to consider is if you do collaborative, right, that's the scenarios where people work closely with the robot. And that was one of the first things they addressed in the collaborative robot scene, right? They wanted it to be safe. And what does that mean in 3D? It also means something, because normally what was used was laser systems. And that's great product, right? They can see very long and everything. And when you think of it, it was used for the automotive, inside cages where the robot was working apart from humans, and then it's not such a big problem. But when you start to go next to the work cell, and think of it if you have like very shiny objects, and you have a dangerous laser and it can get reflection, so it starts to count then. And then, so it's a thing you need to consider. What sort of light source is actually inside this camera, and is it A-safe, or would you need some other protection equipment? So that's a new thing that comes up because of the collaborative environment. And then another thing is colors. Traditionally, 3D was only kind of depth data. You get 3D point cloud, but there is no color. Could be, in some cases, you get a 2D image as well, but that's grayscale mostly. Then the Kinect came out with the RGBD camera in 2011, the first Kinect. It started like a wave, you know, the research and everything, they adopted it very quickly. So it's happening. The reason it wasn't color before is because it wasn't needed, right? The industry had the machine parts, mostly metal, aluminum, whatever, so there's not much color there. But now, I mean, in logistic and everything, then color start to be more important. And as you can see, there's lots of information in color. So when you kind of add the color, you suddenly start to see a different picture. And if you have lots of types of objects, like you would have in these kind of scenarios, then this is important thing to consider. So, yeah, it's kind of Amazon scenarios where there might be millions of SKUs and you have AI type of algorithms to do the recognition, then you need all the information you can get to train it correctly. So there is, to summarize, there is 3 different things we think is like kind of overall thing needs to be considered. First of all is image quality, and it's image quality in regard to what you are going to do. And then the technology choice can, I mean, if you're going to do robot motion for a mobile robot, then some technology is better for that. And if you're going to do picking, some are better for that, and so on. So, and then if you're doing high quality bin picking where you have lots of objects inside and robot collision can be a big problem, you need more accurate vision system. And then there is no better vision system for close range if you need high accuracy than structured light. It's considered the most accurate. Going longer distance, it's not the best. And then, of course, smaller object will need more accurate vision in general. And then also be very notorious about looking at the specification. What sort of condition is this specification for? What does happen when you image not optimal surfaces, kind of like the real world objects and things like that. So this is important thing to look at. Then it's about flexibility. It depends. I mean, in general, before you just mounted the camera statically, and that's fine, and it was like that for and it did the same operation all the time. But But now we see more scenarios where it's more needed with flexibility. A certain scenario could be a mobile robot that picks, from shelves in a facility, where suddenly you would need the ability to mount the camera on the robot, and things like that. And then just mounting on a robot can be done, of course, but then you need to consider, okay, there's vibrations, there's potential shocks, there's a lot of other things that doesn't reveal themselves in the lab, but over time they will kind of start to matter. So these things need to be considered. And last thing, in collaborative is safe and need to be considered as well. And then need to take consideration around laser, because laser it can also be safe lasers, but often it's on the dangerous side if you want to look longer with laser. So it's something to consider. Yeah. So that was all. I think I followed the time very well. So it's time for some questions.
Thank you.